Carl Friedrich Gauss. Born in 1777 in Brunswick, Germany, Gauss displayed extraordinary mathematical talent from childhood. At age 3, he corrected his father's arithmetic calculations. By 10, he had discovered the formula for summing arithmetic sequences. His doctoral dissertation in 1799 provided the first rigorous proof of the fundamental theorem of algebra, establishing that every polynomial equation has at least one complex root. In 1801, he published Disquisitiones Arithmeticae, which revolutionized number theory and introduced modular arithmetic. The work established congruence notation and proved the law of quadratic reciprocity, one of number theory's most important results. Gauss made groundbreaking contributions to differential geometry, developing the theory of curved surfaces and introducing Gaussian curvature. His Theorema Egregium proved that curvature is an intrinsic property of surfaces, independent of how they sit in space. This work laid mathematical foundations for Einstein's general relativity. In astronomy, Gauss calculated the orbit of the asteroid Ceres using only 3 observations, developing the method of least squares in the process. This statistical technique remains fundamental across scientific disciplines. His contributions to magnetism and electricity, formalized in Gauss's law, bridged mathematics and physics. He worked on non-Euclidean geometry, but never published these results, fearing controversy. After his death in 1855, his private notebooks revealed he had anticipated many later discoveries. Leonhard Euler. Born in Basel, Switzerland in 1707, Euler became the most prolific mathematician in history. He studied under Johann Bernoulli and produced over 800 publications spanning nearly every mathematical field. Euler revolutionized mathematical notation, introducing symbols that became universal standards. E for the natural logarithm base, I for the imaginary unit, f of x for function notation, and sigma for summation. These conventions transformed how mathematics is written and communicated. His work in analysis was foundational. He developed the calculus of variations, solved the Basel problem by proving the sum of reciprocals of perfect squares equals pi squared over 6, and derived the Euler-Mascheroni constant. The Euler identity, e to the power of I pi plus 1 equals 0, elegantly connects 5 fundamental mathematical constants. In topology, Euler solved the 7 bridges of Königsberg problem, effectively founding graph theory. His formula V minus E plus F equals 2 for polyhedra established the field of topology. He made fundamental advances in number theory, proving Fermat's little theorem and studying perfect numbers and prime distributions. Euler transformed mechanics and fluid dynamics through the Euler equations, which describe fluid flow. After becoming completely blind in 1766, he worked until his death in 1783, leaving a legacy that touches virtually every branch of mathematics. Bernhard Riemann. Born in 1826 in the Kingdom of Hanover, Riemann revolutionized mathematics despite a short career cut short by tuberculosis. He studied under Gauss at Göttingen and produced work of exceptional depth. His 1854 habilitation lecture, On the Hypotheses Which Lie at the Foundations of Geometry, introduced Riemannian geometry. This framework generalized Euclidean geometry to curved spaces of arbitrary dimension, introducing the Riemann curvature tensor. 60 years later, Einstein used Riemannian geometry as the mathematical foundation for general relativity, describing gravity as space-time curvature. In complex analysis, Riemann developed the theory of Riemann surfaces, providing geometric understanding of multi-valued complex functions. He introduced the Riemann mapping theorem and studied conformal mappings, establishing complex analysis as a rigorous discipline. His 1859 paper, On the Number of Primes Less than a Given Magnitude, introduced the Riemann zeta function and proposed the Riemann hypothesis. All non-trivial zeros of the zeta function have real part 1/2. This conjecture remains unproven and is considered mathematics' most important unsolved problem, with profound implications for prime number distribution. Riemann contributed to mathematical physics through his work on partial differential equations, heat conduction, and shock waves. The Riemann integral provided a rigorous foundation for integration theory. His approach to functions of complex variables opened new mathematical territories. Despite dying at 39 in 1866, Riemann's ideas fundamentally reshaped geometry, analysis, and number theory, creating mathematical structures that continue driving research. David Hilbert. Born in 1862 in Königsberg, Prussia, Hilbert dominated early 20th century mathematics through technical achievements and visionary problem setting. At Göttingen, he created an intellectual center that attracted the era's finest mathematical minds. His work on invariant theory in the 1890s revolutionized the field by proving existence theorems without explicit construction, introducing a new level of abstraction. His Grundlagen der Geometrie, Foundations of Geometry, in 1899 rigorously axiomatized Euclidean geometry, clarifying logical dependencies between geometric axioms. At the 1900 International Congress of Mathematicians in Paris, Hilbert presented 23 unsolved problems that guided mathematical research throughout the century. These problems spanned number theory, algebra, analysis, and mathematical physics. Solving even one earned lasting recognition. The Hilbert problems demonstrated his insight into which questions would prove most fruitful. Hilbert introduced the concept of Hilbert spaces, infinite-dimensional generalizations of Euclidean space, that became central to functional analysis and quantum mechanics. His work provided the mathematical framework for Heisenberg's uncertainty principle and Schrödinger's wave equation. In mathematical logic, Hilbert championed formalism, the view that mathematics consists of manipulating symbols according to specified rules. His program aimed to prove consistency of mathematics using finitary methods, though Gödel's incompleteness theorems showed limitations of this program. Hilbert's approach profoundly influenced logic and foundations. He contributed to integral equations, calculus of variations, and relativity theory. He died in 1943, having shaped mathematics' direction through technical mastery and strategic vision. Isaac Newton. Born in 1642 in Lincolnshire, England, Newton transformed natural philosophy through his unification of mathematics and physical science. During the plague years of 1665 to 66, while isolated at his family home, the 23-year-old Newton developed the foundations of calculus, formulated laws of motion and gravitation, and conducted experiments in optics. His method of fluxions and fluents provided systematic techniques for differentiation and integration, though priority disputes with Leibniz over calculus's invention created lasting controversy. In 1687, Newton published Philosophiae Naturalis Principia Mathematica, arguably the most influential scientific work ever written. The Principia presented his three laws of motion and the law of universal gravitation, showing that the same force governing falling apples also governs planetary motion. Using geometric methods and calculus, he derived Kepler's laws of planetary motion from gravitational principles and explained tides, precession of equinoxes, and comet trajectories. Newton's mathematical contributions extended beyond calculus. He developed methods for approximating roots of equations, classified cubic curves, and contributed to finite differences and interpolation. His binomial theorem generalized to non-integer exponents, expanding the scope of algebraic manipulation. In optics, Newton's experiments with prisms demonstrated that white light comprises a spectrum of colors. He built the first reflecting telescope, designed to avoid chromatic aberration. His optics explored light's nature and introduced queries about light particles versus waves, stimulating centuries of debate. Newton served as Lucasian Professor at Cambridge, Master of the Royal Mint, and President of the Royal Society. His personality was complex, intensely private, often vindictive toward rivals, yet capable of profound insight. He died in 1727, having established the mathematical framework for classical physics that dominated until Einstein's relativity. Évariste Galois. Born in 1811 near Paris, Galois compressed revolutionary mathematical discoveries into a tragically brief life. He developed group theory and Galois theory, solving problems that had puzzled mathematicians for centuries. His work answered the ancient question of which polynomial equations can be solved using radicals, formulas involving only arithmetic operations, and root extractions. Galois introduced the concept of groups to study permutations of polynomial roots. He showed that a polynomial equation is solvable by radicals if and only if its Galois group is solvable in a specific group-theoretic sense. This connected abstract algebra to classical equation theory, revealing deep structural relationships. His insight that symmetries of equations determine solvability opened entirely new mathematical territory. The general quintic equation has no radical formula because its symmetry group, S5, is not solvable. This explained why centuries of attempts to find such formulas had failed. Galois theory became fundamental to modern algebra, influencing field theory, algebraic number theory, and algebraic geometry. The concept of groups extended far beyond Galois' original application, becoming central to mathematics and physics. Galois' life was turbulent. He failed entrance exams to École Polytechnique, was expelled from École Normale for political activities, and was imprisoned for Republican activism. The French Academy twice rejected his mathematical work, failing to recognize its importance. On May 30th, 1832, the 20-year-old Galois fought a duel, reportedly over a woman. The night before, knowing he might die, he wrote feverish letters explaining his mathematical discoveries, noting, "I have not time," in margins. He died from his wounds the next day. Galois' manuscripts were published in 1846 by Louville, 14 years posthumously. Mathematicians gradually realized the depth of his contributions. His ability to see fundamental mathematical structures that eluded contemporary mathematicians, despite minimal formal training, and dying at 20, marks him as one of history's most remarkable mathematical minds. Srinivasa Ramanujan. Born in 1887 in Erode, India, Ramanujan developed extraordinary mathematical intuition with virtually no formal training. Growing up in poverty, he worked through outdated mathematics textbooks and filled notebooks with thousands of theorems, formulas, and results he discovered independently. His mathematical style was unique. He stated results without proof, often arriving at formulas through intuition that seemed almost mystical. In 1913, Ramanujan sent a letter to G.H. Hardy at Cambridge containing pages of mathematical theorems. Hardy, initially skeptical, recognized genius in results that were scarcely possible to believe. Hardy arranged for Ramanujan to come to Cambridge in 1914, beginning an extraordinary collaboration. At Cambridge, Ramanujan produced groundbreaking work in number theory, infinite series, continued fractions, and partition theory. He discovered properties of the partition function p of n, which counts ways to write n as a sum of positive integers. The Hardy-Ramanujan asymptotic formula for partitions demonstrated deep connections between analysis and combinatorics. Ramanujan contributed Mach theta functions, which remained mysterious until connections to modern physics and representation theory emerged decades later. His work on modular forms and elliptic functions anticipated later developments in string theory. The Rogers-Ramanujan identities connect partition theory to Q-series in unexpected ways. His notebooks contained results on hypergeometric series, infinite radicals, and definite integrals. Many formulas were stated without derivation, and mathematicians spent decades proving them. Some remain only partially understood. Ramanujan attributed his mathematical insights to his family deity, claiming formulas appeared in dreams. He returned to India in 1919, dying in 1920 at age 32. After his death, mathematicians discovered additional notebooks filled with hundreds more results.